Okay, so I want to move on from spin and to a discussion about rotationally symmetric systems, and then to a discussion about orbital angular momentum. And as examples of rotational symmetric system, we are going to discuss two systems. One would be the hydrogen atom. The other one would be the three-dimensional harmonic oscillator. So I might abbreviate our discussion of the three-dimensional harmonic oscillator because we want to move on to other stuff and spend more time discussing the hydrogen atom. Okay. All right. So so before I move on to discuss about rotational symmetric system formally, I wanted to ask you some questions. Suppose that we have a free particle which has some spin. So it's a spin half particle. And so we chose to, and suppose that it's kind of sitting in empty space. There is no magnetic field or anything present. Then, it has, say, some state, psi. And that state is given by a linear combination in terms of m goes from -half to +half. C of m is a coefficient of linear combination, and the basis states are half and m. Okay? So here, by this I mean that if S of z were to act on half of m, it would give us m h bar half of m, okay? So this thing doesn't have to be, this state doesn't have to be in an eigenstate of this. Whether or not this is an eigenstate of this will depend on these coefficients. So, is there something special about this? So let me just change the notation a little bit so that you know that it's in the z basis. So I'm going to put in the z here, right? So for example, now could I have written this in terms of a basis state, which instead of the basis state being eigenstate of z, the basis states were eigenstates of the x operator. Right? Could I have done that? Could I have expressed psi in terms of these things?
So no, maybe. So the reason I thought that probably is they're not compatible with each other, each components of the spin. So we might not have a simultaneous eigenbasis for them. I don't know
Yeah,
if
I'm not
that's...
asking about simultaneous eigenbasis. What I'm saying is that is there an analogous formula like this one, but instead of the basis being the z basis, the basis is the x basis? Could I express psi as a linear combination of these states?
I think it's possible. I remember doing something like this in StatMech. So.
Okay, well, why don't you use more of the physical intuition or the logic that we're using in this course rather than say, oh, I remember doing something like that in StatMech.
Yeah, I'm trying to recollect what I did back then. And yeah, okay.
So, so what would be the physical argument that you can express this as a series So, if you were to express this as a linear combination of this, what would in principle be different? In comparison to this. So, so I want to express psi as a linear combination of this m, x, and there's going to be a psi sum over m. And so what, can you fill in the gap here? So there is dot, 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 there is dot, dot, dot. It's a very, very vague question, but it's a vague on intention because I want you to think. Instead of saying, "Oh, I have a right," try to think physically, right? So remember that we have a particle just sitting in space. There is no magnetic field, electric field, nothing.
So the space is isotropic. So yes, we can.
Yeah, I mean, that's actually not important, but I'm just simplifying the situation.
Oh.
There could be stuff there and it would not change the general answer.
So sir, like my guess would be that the coefficients would remain the same as well as the sum limits.
Right. So the sum limits, you're right, is going to change, right? Is going to be the same, right? Because, even in the x basis, this quantum number is still -1, -half, and +half, right? But this coefficient, if this coefficient, nice if this coefficient would change from this one. What do other people think? So nice said it would not change, sorry.
I think it will change, though I
Okay,
can't give a solid answer why.
can you give me an example from which I can extract a more solid answer?
Yeah, I'm trying to think of a reason why it would not change, or why it will change. I'm trying to think of that, but I can't find one.
Okay, so now let's just put in a coordinate system, right? So we put in a coordinate system. And I can orient this coordinate system in any way I like. And let this be z, and this be x, and this is y. Now, suppose by happenstance, not by design, our state psi happens to be half z, okay? So in that case, what are the values of this c? What is c minus half?
0.
Right, what is c plus half?
1.
Right. So, but you know that this basis vector is related to these basis vectors as well, right? So it is something like, say, half of z. I forget exactly what it is, but that's not important. There's a 1 over square root of 2, I think. Well, it has to be, and then there's a half of x, and then I think there's a plus I or minus I, or actually, no, the I is for y, right? For x, there is no I. Remember? So this is going to be 1 half minus half x, okay? So in this case, so are these coefficients same as these coefficients? Let me write them as, say, let me write this as Cm prime. So are C primes equal to Cm primes in this case, in this particular case? Nahi, what do you think?
Yes, sir.
Are they the same?
No.
Because these are the Cm primes, right? And they're different from this case. So in general, the answer to my questions are yes, of course. This state can be expressed in any basis we like. This basis is no different from this basis, and depending on what the state was and which basis we are choosing to express this, these constants will change. Okay.
So is there a specific condition where the coefficients would be same, like orthogonal or anything else?
Okay, so you said that, is there a specific case where the coefficients would be same? Let me see if we can answer that, right? So let's take this psi. So how would we express it? What would we have to use to express it in a particular basis? I'll give you a hint. Psi can be written as identity operator acting on psi. Okay. So if you have a given basis, then how can we write the identity operator?
The addition of their bases.
In terms of the projection operators, right?
Yeah.
So we can say, okay, we can express it in terms of, say, m goes from minus half to plus half, and this is, say, half m. So this is, and suppose this is in the z basis, which is important for this discussion to denote which basis we are using, times psi. So what are these? These are what I was calling C of m.
Mm-hmm.
So one has other expansion. So the expansion we're using here is in terms of the z basis. But we could have expanded it in a different basis where it is the x basis, right?
Yeah.
So that is also possible. Now let's see, if this is going to be the same under some condition in both bases. So I'm just going to erase this to make room. Actually, I'm just going to copy this. Put it here. Okay. And now what I'm going to do is that I'm going to say, okay, so I have expressed in terms of, now what if I imagine again another operator here, 1, and now let's express that in terms of m prime. So m is just a dummy variable, so whether I call it m or m prime, it doesn't matter. But now I am going to expand this 1 in the x basis, right? M prime, x. Okay. And then this will multiply, which I had before, which was half m of z, and then half m Z psi. Okay. So now what I can do is that I can say, okay, what I can, so this is going to be M prime. And now this is just a complex number we are calling C of M. Now this times this is going to be a change of basis matrix. Let me call it D M prime M. And that's going to be acting on this thing, which is half M prime X. Okay? Now, I could have expressed my original vector psi in the X basis. And if I had done so, then I would have gotten, something like D M prime half M prime X half M prime X psi. And these are constants. Let me call them C prime of M. So this thing is equal to this thing. So here we see the same basis vectors as here. So we can equate the coefficients. If I equate the coefficients, I find that C prime of M is equal to D M prime of M summed over, so see, this should be M prime, right? Yeah, M prime. And summed over M, C of M, right? So this is a linear transformation. This is a matrix equation. Okay?
Yes, sir.
So when will C prime of M be equal to C of M? When will that happen? This will only happen if D of M prime of M is equal to delta Mn, right? Okay?
I see, yeah.
Right? So that means that, so let us go back to what D was, right? D was given by, okay, we should write down what D is explicitly, it's important. D over here was D M prime M was this thing, half M prime of X, half M of Z. So can this ever be, if this is the X basis and this is the Z basis, can this ever satisfy this?
When they're perpendicular?
So you know what the relationship between the X basis and the Z basis is. Can you get, so the X basis, so let's just remind ourselves what this thing is again. D M prime of M is half. We don't have to write half because everything has spin half here, right? So let's just drop the half. Let's just put M prime Z, so M prime X it should be. M prime X and M of Z. Okay, now what is M prime, what is M of MZ in terms of these things, or these are the bras in terms of ket. We know that's given by M, so if M is, depending on the value of M, if M is plus half, So m can be plus half or minus half, right? So this is going to be half of x plus minus 1 over square root of minus half of x, right? And now if I plug one of these guys in here, this thing can either be half x, or it can be minus half x. So if I take the inner product of this and this, will it ever be 0?
No, sir.
Because this thing, the inner product of this thing and this thing will be 0, but the inner product of this guy and this factor is 1, and therefore the inner product of this and this will be 1 over square root of 2. What about the inner product of this and this? Will it ever be 0?
1 over square root of 2.
Sorry?
It's also 1 over square root of 2.
It'll be, minus 1 over square root or whatever, right? Yeah. So we see that the inner product of this inner product can never be 0. Can it be 1?
No, sir, because one of them are orthogonal.
It's always 1 over square root of 2 or minus 1 over square root of 2,
Yes,
right?
sir.
So can D be the delta function?
No.
No, sir.
Then does this answer your question?
Yeah, it doesn't work. Yeah.
Okay. All right, good. So, also think of it physically. So this was a mathematical proof. Think of it physically, right? Physically, what you have is that suppose your state has some direction in space. It doesn't have to be in the z direction, but it is some eigenstate of the n dot s operator, where this is the n direction, okay? This is the n direction, and your state is some eigenstate of this operator, right? So if you choose any direction that is not parallel to this direction, suppose you choose some other direction, say n prime, then if you look at the eigenstates of say n prime dot s operator, the eigenstate of this operator will always be able to expressible in terms of the eigenstate of this operator, and vice versa, right?